So now let's go on to the short answer responses. And the first thing I want you to understand is that I've deliberately left here the lines in place. And why I did that was to show you that you have enough space to solve all of these questions with the space that's provided by the examiner. The questions are in order of difficulty. So question 21 is meant to be relatively easy and they get progressively harder. So here we asked to calculate the frequency of this light. Well, the whole principle here is that C is equal to F lambda. The speed of light is equal to frequency times lambda, and so therefore the frequency is equal to C divided by lambda. C, of course, is 3 by 10 to the power of 8 divided by lambda. It's important here to have the correct SI unit, so we get 5.5 by 10 to the power of -7. This is a common error here that someone could make, and you get 5.45 by 10 to the power of 14 hertz. And there you go. There's first question done. It says the electrons in a specific metal must absorb a minimum of 5 by 10 to the -19 joules in order to be ejected from the surface. So this is the work function. It says explain why electrons will not be ejected from the metal when photons of wavelength 550 nanometers strike the surface. And it says support your answer with relevant calculations. So you can't just say it's not meeting the work function value. So what you do is you work out the actual energy. So energy, of course, is equal to HF. We just established what F was, and so now you have 6.626 by 10 to the power of -34 multiplied by the frequency of 5.45 by 10 to the power of 14. That gives you a value of 3.6 by 10 to the power of -19 joules. That is not sufficient for a full answer. You need to now say this is less than the work function, and therefore no electrons ejected. That would be what you would say. Question 22. A torque is applied to a nut using a wrench as shown. Suggest two ways that are applied torque could be increased. The key here is the formula that's straight in your formula sheet. Torque equals force times distance, where distance is the distance from the pivot point. Well, if that's the case, clearly you can increase the torque, first of all, number one, by increasing the force. That's the first thing. Number two, by increasing the distance. That will also increase the torque. In other words, the hand could be pushing that force on that end. That's all there is to that part of the question. A coil consists of 15 turns and is placed in a uniform 0.2 Tesla magnetic field between two magnets. A current of 7 amps is flowing in the direction as shown, which is right there. Calculate the magnitude and direction of the torque produced by the side BC of the 15-turn coil. So we're only interested in this aspect right there. So don't use Bain here, because Bain accommodates both sides. So all you need to work out again is that the torque is equal to the force times the distance. But of course the force is actually Bill. Sine theta, but of course here it is 90 degrees, so we'll ignore the sine theta, multiplied by the distance. But it also has to include the number of turns. For every turn you increase the torque by that factor. So let's put everything into place now, substituting into a correct equation. B is 0.2. Notice I put brackets around it, so I basically separate all my values out. I is 7. L is this length, which is 0.08. D, now this is 0.06, so D here is 0.03. And then of course I have the number of turns, which is equal to 15. If I calculate that out, I get 0.0504, or really 0.05 Newton meters. That is only part of the question, because it says not only the magnitude but also the direction, and since the current is going up here, the current must be going down here, and using your right hand rule, that means on that side it is going into the page. This is a longer response question. It says use examples from special relativity, explain how theories in science are validated or supported in different ways. It's important you need to understand we can only use examples of special relativity. We need to explain, so we're looking cause and effect, and finally we're looking at different ways. So we need to find 3 different ways that special relativity has been validated. And the first way we can look at is basically direct experimental design. So experimental evidence. Experiments have been designed to test the various theories. And the example you could use in this case is the atomic clocks on the plane. And those, of course, you need to talk about that a bit further. You need to talk about the fact that they're going in different directions. And as a result, we show time dilation. That's the cause and effect of that particular thing. So this experiment validates special relativity. Number two, another thing is that we could have observations that can only be explained by special relativity. And in this case, I would use the example of the muon. So muons, of course, are subatomic particles that are created in the upper levels of the atmosphere, and they have a very, very short half-life. And by rights, by normal classical physics, we shouldn't be able to detect many of them at all at the surface of the Earth. But we do. But we can explain that by time dilation. So again, as long as you understand that muons have half-lives that are short, and then talk about the fact that they do make it, we are able to detect them, you're getting the cause and effect here, that shows, again, time dilation. Again, cause and effect. And the third way science is validated is that we make allowances in technology. One for a better word. So, for example, a good example is our GPS satellites. Our GPS satellites, the clocks are specifically run fast. Why is that? Well, because they're moving fast in orbit, they are going to go undergoing time dilation, but GPS requires accurate timing between ground-based equipment and the satellites, so you need them to have exactly the same time. Now, the reality is that GPS satellites are also affected by gravitational issues, and that's general relativity, but this is sufficient to understand the fact, again, we now explain how GPS satellites show and validate special relativity, and in this case by allowances for technology. So there are three examples. As long as you got a few examples, and we have definitely an explanation here, then that you should be able to get the 5 marks. You don't necessarily have to do all three, but you just need to see you've got different ways that we can validate science. The next question is a relatively easy question. The first part says the escape velocity of a planet is given by this formula here. It's actually interesting that they've provided you the actual formula, because in previous papers sometimes you actually need to calculate it out. The radius of the Mars is given by this value and its mass is this value. It's just calculate the escape velocity. This is a simple plug and chug question. So all you have to do is say, here's the formula, 2gm over r. You then substitute the values in, so you get the square root of 2 multiplied by g, which is 6.67 by 10 to the power of negative 11. Multiply that, of course, by the mass, which is 6.39 by 10 to the power of 23. And then divide this, of course, by the radius, which is 3.39 multiplied by 10 to the power of 6. And when you calculate that out, you get 5,014 meters per second, and that's your final answer. Fairly easy question. But B is a little bit harder. It says use the law of conservation of energy to show that the escape velocity of an object is independent of mass. So you need to understand this. And the key here is that if you are escaping gravity, you are increasing the gravitational potential energy. You are gaining gravitational potential energy. That, of course, means a loss by the kinetic energy. In other words, the object will slow down. Of course, this is all about law of conservation of energy. You need to be explicit about saying that. But then you're in the position to say, well, hold on, what is therefore the minimum amount of kinetic energy I can give so that it will leave? And the way you do that, of course, is say, well, what's the minimum? It's when GPE is equal to KE. And when you work that out, you get GM1 M2 over R, that is the gravitational potential energy increase, as equal to the half mv squared. And because the energy, of course, is a scalar quantity, you can leave out any negatives. We're only interested in the actual change. And when you see that, you can see that this mass is the mass of the object in question. This mass is the object in question. You can therefore cancel this out. Therefore, you get a formula that says Gm over R is equal to a half V squared. That of course ends up being that formula up here. But you can see now that mass being cancelling out is therefore independent. You've shown this aspect right there. Question 25. Outline the contribution of Bragg's to the scientific understanding of materials. Outline is sketch in general terms. So what we're looking first and foremost is that they used X-rays and they fired at crystals. They ended up getting interference patterns. These interference patterns, of course, were regular, and that therefore allowed them to work out the fact that the atomic arrangement was regular, but the better word, of course, is in a lattice. And subsequently, of course, when we do this with metals, we get the same thing. Question B, explain how doping pure silicon with boron changes its electrical properties. So we really need to talk about explanation, which is cause and effect. The first thing you need to state, of course, is boron is a group 3 element. By inserting boron and replacing a few of the silicon atoms, what you end up getting is the production of a hole. Basically, we have 3 of the valency electrons using for bonding, and we have an empty space. And so we get these holes here. Of course, those holes means you now have conduction possible in the valency band. Not only that, you have a huge increase of holes without the need for heating up to cause electrons to jump to the conduction band. And increasing the holes means increasing the conduction. And so therefore I've changed its electrical properties. I've increased its conductivity, and I could also ask, you could say, I've decreased its resistance as a result. Lastly, outline reasons why superconductors are used on board maglev trains. Well, you need to outline, so it's sketch in general terms. And so we need to first identify, and then we can outline after that. So first of all, superconductors have zero resistance as long as they are below critical temperature. That, of course, we have very high B fields, magnetic fields. That means we could have very large repulsive forces. And that means, of course, in maglev trains, we can use that for levitation and also, of course, also propulsion. And then finally, of course, that means in the end, we have the ability for motion with no friction involved, at least in terms of the contacts between the magnets, or very low friction. There are guiding wheels as well, but they will only contribute a really, really small proportion of friction. So you have really high propulsion as a result. So there's this outline point there. Outline the consequences of a crewed spacecraft re-entering Earth's atmosphere at an angle greater than 10 degrees. Okay, the first thing is to outline, so sketch in general terms. You don't need mathematical physics here. Understand that it is plural consequences, and it's crewed spacecraft, so we're really interested in the astronaut. And there are really only 2 things that are going to happen. The first of all is that at greater than 10 degrees, you're going to have very high acceleration. In other words, the spacecraft is going to slow down really, really quickly. That gives us 2 outcomes. First of all is heat with the atmosphere. And that, of course, means you burn up our astronauts. So that's not really good. Secondly, you're going to have high G-forces on our astronaut. Now, our astronauts can only cope with a certain amount of G-forces, but you're going to have so high G-forces that this will kill them. I mean, if you have G-forces that are way and way in excess of even high impact collisions, then clearly that's not good. Your body are not going to cope. Now, you could talk about the physics of that, but the question is outline, so I don't need to go into cause and effect. This would be okay for this question. Question part B. When a 100-ton space shuttle re-entered the Earth's atmosphere from its orbit, the gases compressed in front of the decelerating shuttle reaches a temperature of 5,000 Kelvin. The graph shows the intensity of radiation emitted by gases at 5,000 Kelvin. Relate the information in this graph to the energy changes required for the shuttle to make a safe landing. Well, the first thing about this graph is that we have this intensity of light here, and the area underneath the actual blackbody curve is the total energy output. So what we're getting here is a lot of energy radiated from the gases here. Now that energy has to come from somewhere by the law of conservation of energy. Now we can also work out the energy per photon as well here, because there is a calculation that could be made here. So if you work out the frequency from this particular situation here, you work out that the energy can be worked out by E equals HC over lambda, and so you could work out the actual energy per photon if you wanted to. The point is though, since we have a huge increase in energy basically produced by the gases, therefore the space shuttle must have a huge decrease in energy as a result. That's needed to slow down. So we need to elaborate a little bit more. This is a clearer question. It's relating the information required to make a safe landing. So you need to be more specific than that to get that 4 marks. So first of all, when a shuttle is in orbit, its orbital velocity may be of the order of around 7,000 meters per second, and so therefore its kinetic energy can be worked out, if you wanted to do so, by equal to half mv squared. It'll be quite a large value. However, when it's landing, its velocity may be of the order of around 20 to 50 meters per second. You can see there's a significant decrease in velocity, and because of it's a square relationship, that means a hugely significant decrease in kinetic energy as a result. That kinetic energy to decrease must go somewhere, so therefore we have to have energy increase somewhere else, and that is in this graph related over here. So I'd imagine that's the solution to that particular question. I don't think you need to work anything with a 100-ton spacecraft, because what we don't have is the actual velocity values given in this situation to determine that as well. The fact that the gas is at 5,000 Kelvin tells you that this is the most predominant amount of energy released, and it's in the visible spectrum, and that's why we have the fact that we have it glowing probably as it goes down into the atmosphere, and it explains why we have the heating up from part A. Question 27. This is all about flux. So we have here a more difficult question, and now not only do you have to interpret a diagram, you have to interpret a graph, which is a much higher order question. And the first part of the question says is calculate the maximum magnetic field strength with the stationary loop during the 12-second interval. Flux is equal to BA, or the magnetic field strength multiplied by the area. And so therefore the magnetic field strength is equal to the flux divided by the area. Now the flux in this case is equal to 0.6, and the area of course is pi r squared. Now pi r squared, r of course is equal to 0.3. So we have pi multiplied by 0.3 squared. And if you calculate that out, you get 2.12 Tesla. Part B requires a little bit more thinking. It says calculate the maximum voltage generated in the circuit by the changing flux. Now it says the maximum. So where along this graph do we have maximum changing flux? Well, it's about the rate of change of flux. So you look at the slope. So here the slope is increasing, here the slope is decreasing, but clearly the slope here is decreasing at a much steeper rate. So therefore this is the area we are interested in. And so what we want to do here is to work out the rate of change of flux. So the EMF is equal to negative delta phi over t. That negative of course is due to Lenz's law. The flux change over this time is clearly only 0.6. The time change here is 2 seconds. And so as a result we get 0.3 volts as our maximum range change of flux. Now the important thing is that this slope is negative, but of course the EMF is negative that, so therefore this needs to be a positive value. If you worked it out over here, then the voltage would be negative here. So it says in your answer indicate the polarity of the terminals So now what we need to do is to work out which side is positive and which side is negative. Now, the fact that this is negative means we have a weakening flux. It's got to go weaker. So in that sense, these crosses are going to go further and further spaced apart. So in other words, we can say that these crosses are heading in that direction, which means relatively speaking, my wire is heading in that direction. Now, if you then use your hand rules to determine the direction of the EMF, then what you end up getting is the current will be going in that direction. Now, if the current is going in that direction, then you know this is going to be my positive terminal and this is going to be my negative terminal. So therefore P is negative and Q is positive. Question 28. It says contrast the design of transformers and magnetic braking systems in terms of the effects that eddy currents have on these devices. So first of all, it's contrast. So you look at differences. You got to look at the design of transformers and magnetic braking systems. And it says the effects of eddy currents. So there are different effects of eddy currents in these devices. So in order to start this question, you need to understand is that eddy currents, of course, are due to a change of flux over time. Now in transformers, this occurs in the iron core. Now the iron core, of course, is designed to increase the magnetic field strength. However, the iron core is experiencing a rapid change of flux, so you get eddy currents in these iron core, and that of course causes it to heat up. That means, of course, we laminate it to reduce that. So here's our effect. We have actually a negative issue with the eddy currents in transformers because that actually causes the heat up, and as a result we have some power loss. What about magnetic braking? Now again, we have metal experiencing a change of flux. However, in this case, our eddy currents that are produced as a result, now although they do produce some heat in the material, what we're interested in, it produces its own magnetic field. It produces its own polarity. That, of course, due to Lenz's law, opposes the motion, and that of course leads to braking. So now we have the effect in this case of a magnetic field, but this now is actually a positive attribute of eddy currents. It's actually helpful in this case. We've talked about the design in both situations. We've talked about the fact that there is an effect that is different, heat as opposed to polarity. We've talked about also the fact that this is a negative consequence and this is a positive consequence, and we've talked about what that actually does in these devices. So I would argue that is what is required to give you a 6 marks response. Here we have a projectile motion problem, and it introduces the whole concept of springs. Now, springs is a whole area of physics that is not in the HSC syllabus, but it actually tells you a little bit, is that the spring will experience a force and it's determined by the displacement. And you're actually given that the kinetic energy that a spring might provide is equal to half kx squared, where k is the spring constant, and it is the slope to this line. And using this information, you're asked, okay, I'm going to launch a projectile using this spring, and it's launched, and you have to calculate the launch velocity. And the key thing to remember is that whatever energy you store over here will be the energy you provide to the projectile in terms of its kinetic energy, and that is the key. So really what you're saying is that the kinetic energy due to the spring will be equal to the kinetic energy due to the projectile. So what you end up getting is a half kx squared is equal to a half mv squared because of conservation of energy. But we need to know k. So you go over here and we need to work out k. And so I'm going to choose this spot over here, and I'm going to choose this spot there because it is a valuable point at equilibrium, that is when the spring is relaxed, no force at no displacement. And so if I work out the rise over run, I'm going to get 18 over rise over run, which is 0.06, And so that gives me a K value of 300. So now I just go substitute this thing over here in. And so I get half multiplied by K, which is 300, multiplied by X. Now we're told here that the compression is 0.08. So I put this in here. And of course that is squared. And that is equal to a half multiplied by the mass, which is given by 0.04, multiplied by V squared. And that's what we're interested in, the launch velocity. We can cancel out the halves. And you can see now I get V squared is equal to 300 multiplied by 0.08 all squared all over 0.04, and that gives me an answer of 48. And so therefore V becomes 6.93 meters per second. So there's my answer. Part B, it says calculate the range of the projectile launched by this device from ground level at an angle 60 degrees to the horizontal with a velocity of 10 meters per second. The fact is that part B gives you the value of 10. You don't need to use the previous value, and that's why I have not included the diagram here. It's not necessary. It's a simple projectile motion problem. And like all projectile motion problems, you divide them up into vertical and horizontal components because they are independent of each other. So do V, U, A, R, and T, and do the same thing on the other side, V average, R, X, and T, and of course we now put in all the variables that we know and the variables that we are determining. We don't need the final velocity, so we're ignoring that. The initial velocity we are told is 10, but it's at an angle of 60 degrees, so you multiply that by sine 60, so that gives us 5√3 meters per second. The acceleration, of course, is negative 9.8 meters per second squared. The range, it goes up and down. We're told it's from ground level, okay? So therefore, we're going to get a range of 0. We don't know T, and we need to know T. Over here, the average velocity horizontally is 10 meters per second multiplied by the cos of 60, and that gives me equal to 5 meters per second. The range is what I'm interested in, and of course this T is the T that I calculate over here. So I'm going to use R is equal to UT plus a half AT squared. Substituting correctly, I get 0 is equal to 5√3 multiplied by T plus a half A. That's going to be equal to negative 4.9. I just put that in straight away, multiplied by T squared. If I rearrange that, I get T outside of 5√3 plus negative 4.9 T. You clearly see, of course, that T either is 0 or some other value. So that makes the final answer 1.767 seconds. Now that time, of course, goes up to here. So this time for the horizontal is still 1.767 seconds. So then now to work out the range, it's simply equal to the velocity multiplied by the time. The velocity, of course, is equal to 5. The time is 1.767. And so that gives us a grand total of 8.84 meters. And there we have it. We now come to the last question, and this talks about analyze the motion of the proton after the fields have been turned on. This is not a question with numbers, so this is really a thinking experiment. And we need to understand what happens to the proton first from the electric field perspective, and then what the magnetic field is perspective, and then sort of try to work out what's going on when both are combined. So let's first talk about the electric field only. What happens when this proton, remember this proton is moving vertically up and it's experiencing an electric field and a magnetic field at the same time. We're not told the strength of either fields, so we don't know those things, but we all do know that this will affect the motion of the proton. So the first of all thing is to understand is that the electric field will cause the proton to accelerate. So the proton will accelerate, but always in the direction of the electric field. So the proton accelerates in this direction. Now, the fact is, of course, that the proton is still traveling in the upward direction, but that is independent of what's happening here. So we have acceleration happening in that direction. We have the proton still moving vertically here. So what you end up getting is a parabola, because you have acceleration, a constant acceleration, because F is equal to EQ. And we know that E is constant and Q is constant. So we have a nice parabola that is in the plane of the paper, so like so. So now let's look at the B field. Now this is a little bit more complex. So again, there's going to be a force on my proton. So my proton is going to still be moving upward, but now it's experiencing a force, of course, that's equal to QVB, and that's going to go out of the page. But because that will cause the proton to change direction, this will cause it to go in a circular path. And that circle is going to be in the plane that is across like so. So in other words, if we were to look at this situation as everything is going into the page, like so, then what we're going to get is our proton is going to go initially up, of course it's changed direction, and of course the force will always be perpendicular, so it will go in a circle, simply by the fact that this is a magnetic field. But remember, the electric field is causing it to accelerate down. And so when you get the two happening at the same time, you're going to get a spiraling going on. But because it's accelerating, that spiral is going to get wider and wider and wider. So there is the answer to question 30, probably the most difficult question in the HSC and probably one of the more difficult ones I have seen in quite a few years. Anyway, I hope that has helped you understand the HSC 2017 paper. Please like, share and subscribe and follow me. Thanks for watching. I'm Paul from High School Physics Explained. Till next time, bye for now.